what we're going to be going over here is what they refer to as the gradient path or the gradient vector here, and we're going to look at it in terms of the production function, and our production function is going to be similar to the Cobb-Douglas production function. Okay, so this is the production function we have here. We're going to have some output here showing Q here, and that's really dollar amounts here, or a profit that we'd be looking at here, and we're going to have some targeted amount here of a profit here, and then that's going to be derived by looking at our units parameter here is 1400, or that's the revenue here, $1,400 per unit we're selling our product for. Then we take that times the material and the labor that we're going to be using here. So the material here, I'm showing both of those in exponential amount or exponents up here. So our material represents about 50.3% of our revenue here per unit of $1,400. That's really raised to the exponent here, 0.5035. And then you take that material quantity here times your labor quantity here, and that labor will raise to about 0.3215 here, or it represents about 32% of the revenue per unit. Okay, so looking at our production function here, first off, looking at it in terms of a 3D output here, and I've got everything done here, and I plotted everything out in all my calculations I've done with MapleSoft. Okay, so first off, for our production function here, that I'm showing here in this blue 3D blue area here, and then those red lines I'm showing here, those are the equal product or the level curve here, and then this red line that moves right up here from a zero input for material and labor. Incidentally, our labor I'm showing over in this axis, lower axis here, and material over in this side on this axis. So this our gradient path here is this red line that starts out here at zero inputs, and then as we increase our inputs in material and labor, it moves actually curved up here or in a straight pattern. And that gradient path, that is the path of our greatest increase here in our output or our production function. Okay, so that's our gradient path here shown in red, but our inputs here, this is really where we're going to be looking at those, our gradient or gradient vectors here, those gradient lines here. So for material, in this case, we're going to be looking at it in our example, we're going to have 70 units here of material inputs. So that follows up here along that yellow line here until it intersects our output here. And I've done a linear program here where I have a targeted output. Actually, it was come up with the solution here, $48,144 here, and that's a targeted output here based on 78 units of labor that we're adding to it and 70 units of material that we're using here to come up with the total targeted profit here, or output of 48,144, and that targeted point here intersects on our gradient path here of the greatest increase, because I've done a linear programming analysis to determine that. Okay, and then so we've got our material gradient going up here, that level line here, and what we really want to look at here is the slope, where we start out here with our initial units that we've added here, and as we move up here, in this case that 70 units, we're up actually at this point here, we have a lesser and lesser slope, or we're adding less and less to our profit. And then same here for labor here, I got it shown at 78. Now remember, these 78 units here for labor and 70 units for material, they really represent this point here of on our gradient path here of an output of $48,144. Okay, so that's our targeted point. But then you see this green plane in here. That's actually slicing through our production function exactly at our targeted output here of $48,144 here. Okay, so this is really what we're going to be looking at. We're going to be looking at these yellow gradient lines here where they converge at our targeted output, and then also look at our slicing through our targeted output here based on our gradient vector here, our equal product line that we're going to be looking at. Okay, so we looked at it in 3D, so let's move over here and look at it in 2D here. So this is really the gradient plot here, and it'd be a gradient vector plot here, again done in MapleSoft. So along our vertical axis here, we're increasing our labor inputs this way, And then along our horizontal axis here, this is where we're increasing our material inputs here. So I got them both shown here at 70 units of material, 78 units of labor here. And this is that targeted output here, $48,144. Now that lines exactly here on our gradient path here of the greatest increase here. I'm showing it here based on our vectors here. I plotted it out here in 2D. So what you're seeing here in 3D here, this red gradient path here, and gradient path is really the path of the greatest increase here in this case, our production function. So red over here, that's our greatest increase here. That's what we're following along here. And then it would be the green over in our 2D plot here. And then this is our targeted output that we looked at, that 78 units of labor, 70 units of material here. And it follows on our gradient path here shown in green. And then this blue curve here, that's our equal product or our level curve here for that exact output here, $48,144 based on labor and material inputs here. Okay, so that's where we're working from now. What we're doing with this gradient plot, those arrows here, really what you want to do is you want to look at the direction of those arrows here, both the length of the arrows and the direction they're going in. So you can see where you start out over here with lower inputs here of material and labor. The arrows sort of go this way, and then they kind of curve up here and they follow along our gradient path here of greatest increase. They kind of curve up and they'll follow along in the direction here of our greatest increase here, and that's the gradient path that we're looking at. And that's true for both sides of these, looking at your material here and your labor here. So just remember this blue line here, that's our level curve or equal product curve. So really you got, regardless if you have a lesser degree of material, more labor, you're going to come up with the same output here if you follow along this curve here. But if you're looking for material and labor here, you're going to be looking for some constant amount that you're going to be looking at. And you want to see where you're deviating based on your gradient path here of greatest increase and also your gradient curve here, or equal product curve. Okay, so the blue line here, equal product curve, matches up with our green cutting plane that's going through our production function here. Okay, so that's just our first gradient path or plot that we're looking at with these vector amounts. Now let's just move over here. Now maybe it's a little easier to see here with our gradient plot here. Now really this is the change in slope of our material and labor here. So again, instead I've got bigger arrows here. So what's plotted out here is you got these bigger arrows here, longer and bigger here. That means you're getting a greater increase here based on your combination here of material and labor here. And you can see the direction they're moving in. And then as you increase your output here, or you increase the material and labor amounts, you can see the arrows become smaller and smaller and smaller. That means the slope here is less and less and less. The slope here is greater with your lower increases of material and labor, and you're adding more and more to your production output or your production function here. And again, just looking at it. So these gradient path plots here in 2D are kind of useful here because you can see your level curves here, these light blue lines here are the level curves, and then again this blue line I'm showing here is that cutting plane, or we're going through here based on our targeted output here, 48,144, and that's actually our gradient, that's where our gradient vector is meet right here. But this is gives you an idea what's going on here when you look at your equal product curves here. So the blue line here represents our gradient or our intersecting gradient equal product curve here at that particular point. So the red point here matches our gold point over here in our gradient plot. Okay, so that's basically what these plots look like and how they really can pictorially tell you what you're doing here with your production function. When you have lower inputs here in combinations of material and labor, you're going to have, in this case of our production function, you're going to have greater value added to your output here for material and labor. And the more and more you increase your output here, you're getting less and less, based on our production function here, less and less increases here in output based on adding more material and labor. Okay, so let's just go down here and look at our other case. So we'll just look at a profile here in 3D of that gradient path that we're looking up in red here. So I'm just showing it in blue here, but you can see the production function here as it's increasing here. So down over in this area, this is where you had your greater output with material and labor here. And you get, if you looked at it from the side angles here, you're going to see where you get your increases. I'm just looking at our total increase here in our production, our gradient path, the path of the greatest increase here. And again, this green line here, that's that level curve here for our gradients based on our targeted output that we have here, 48,144. 70 units of material, 78 units of labor shown here. So green, or the green cutting plane here, that's our level curve based on the output here that we have of $48,144. And then again, material and labor inputs. This yellow curve here, that's just the idea, gives you the cutting plane going through our gradient path in the direction of the gradient path. Okay, so that'll give you some feel for what this level curve is here and how it cuts through our production function here at the particular inputs of material, labor, and at that output. Okay, and then if we move over here, this is what we're going to get to in our calculations here. I'm just showing it in 3D again. So we got our level curve here shown in red. This is our targeted output. And then we got that our gradient inputs here, material and labor. And that's where they converge here at that our targeted output here. What we're going to be looking at, what we want to really, what these gradients, what we're talking about the gradient, is these two vector amounts here. And I'm showing them in arrows here on some tangent plane here. And that really represents at this point the material that output here, or the material that we're outputting here, and the labor that we're using, the material we're using and the labor we're using, how much they're actually contributing to our output exactly at our targeted point here. So what we're going to be looking at is, this is what we're talking about. This gradient vector, these gradient lines here, these yellow ones here, times a directional vector equals our directional derivative, or our output exactly at our targeted point here, based on the labor and material combinations we're looking at. So what we really get down to when we're talking about these gradient vectors, they tie into what they call the directional derivative, or the change in unit output, or the slope exactly at that point here. And that's shown in red here. And it's really the directional derivative, but it's a function of our gradient vector and our directional vector. Taking those times each other here, or dot product, they're going to equal our directional derivative. So next, now we'll go in and we'll just get an idea on how we'd go exactly calculate our gradient vectors here based on our inputs here for material, labor, and our targeted output here sitting on our path, gradient path here of the greatest increase. Okay, now for our calculation. So this is our production function here. So the gradient, or the vector path, remember that's the direction of the greatest increase here. And we determine that by taking the partial derivative of our production function with respect to material and labor here. So okay, so for our production function here shown, we'll review that again here. The gradient path, that's that red line that I'm showing up here. That's the direction of the greatest increase here, shown here. And that gradient path, that's where you have a proportional increase here in material and labor. And then you have these level curves I'm showing in red here. Those are equal product curves. And the gradient vector here is really perpendicular to these level curves. And then these yellow lines here, I was referring to those as the gradient vector. Actually, the gradient vectors at the point here of our targeted output here, based on our inputs here of labor of 78 units and 70 units of material. So what's going on here with these yellow lines? Really, that's the tangent path or the change in slope of material and labor, and you refer to them as the marginal product for both material and labor. So you can see here, looking at it from our material aspect here, you can see it has a very steep slope here when you have your first units here of material that you're adding, but as you move up to the point here, and remember this point here at a targeted output, it is based on exactly 70 units of material and 78 units of labor here. But it's the tangent path really follows the inputs of material and labor up as you go reach your targeted output here at your gradient path. Okay, so the calculations that we have to make here. So we have to take this is our production function, and just to review partial derivatives. Now in this case, I just plugged them into the MapleSoft here, and it gives you the partial derivatives, and it calculates the slopes and the gradients and everything like that. But just to review them by hand here, so just understand that. So here's our production function. So if we take our partial derivative in terms of material, or our x looking at it here, material represents our x value here. So you would do here, you just take your exponent of your x or your material here and take that times your coefficient here, exponent 0.5035 times 1400 gives you 704 here, and then you would subtract 1 from that here. So that gives you, subtracting 1 from 0.5035 gives you x here at 0.4956. It's a negative amount, so it becomes goes into the denominator here. And then in the case of partial derivative here in terms of material, the y value here is held constant, so that remains constant. So what you would do here now for your rate of change, all you do is plug in your labor of 78, material of 70 into your partial derivative, and this is where you get your slope here, a material slope at 347.01 here. So what we're talking about here is at that particular output here that we have for the inputs of material and labor, material is adding $347 to the rate of change at that output. And then for our labor here, do the same thing. I'm not going to go through that here, but you would hold your x quantity here constant, take your y exponent here times your coefficient here, 1400, you're going to get 450, subtract 1 here from your y coefficient, or y exponent, excuse me, and you're going to get what, 0.3215 minus 1 gives you 0.6785 in a negative amount, so it sits in the denominator here in your partial derivatives. Again, just plug in your material here at 70 units and labor here at 78 units, and you're going to get a slope here of 198.85. And that's really the rate of change here based on your input of labor at that point. Okay, so what our gradient vector is, we worked all the way through here. A gradient vector is really taking our gradient here is that vector, and we would take it for our material first here. That's our slope here, $347 or dollars here times the vector amount, plus we would add to it our rate of change here for our labor, 198. So that's our gradient vector here. That's the direction of the greatest increase based on our production function. Okay, so now let's go and let's apply our gradient vector here and see how it fits into, and let's look at it. Okay, so the gradient vector is really a part of our directional derivative or vector, and that's really the point or the slope of a tangent plane in the direction of the point that we're looking at here. And really that's the rate of rate of change here at a specified direction. In our case, our specified direction here is based on 70 units of material and 78 units of labor here. Okay, so looking at it in 3D here, this is our targeted point here. So this red thing is really our directional derivative here, and that's really a product of our directional vector here and the gradient vector here. So these yellow items, really we can look at it in terms of our material and labor inputs here, and they're really part of taking the gradient vector times a directional vector here, and they're going to come up with some amount. So let's go and let's look at how we'd make those calculations. Again, what we have, we start with our gradient. That's our gradient vector here that we have that we just calculated. Now the next thing we have to do is come up with our directional vector here. So based on our units here, material and labor, this is our directional vector we have. We got to bring it down into a unit amount. Directional vector is 70 units of material plus 78 units of labor. But to come up with the unit, we have to come up with a unit quantity. We have to bring it into a unit quantity or look at it. So just take, in the case here of our labor, take 78 here, and you divide into it, and really you're working off this triangular amount here. You're trying to really figure out the hypotenuse here, knowing your material and labor here inputs, and you're just trying to come up with the unit amount here. So for what we would do is just take 70 units here of material, square it, plus add 78 units here of labor, square that, and take the square root of it here. And this is where you're going to get your unit amount here. So you get, this is the unit amount here. So you got your value here, you divide it into your labor, directional vector here for labor, and you're going to get 0.7448 here. So that's your unit amount here for labor. Same, and then just do the same thing for material here. 70 units of material squared plus 78 units of labor squared. And take the square root of that amount and divide it into 70 units here in material, you get 0.667794. So that's the directional derivative unit length, and you have to work with the unit length. So we'll apply that here. So we take, moving over here, we have our gradient vector here, input for material and labor. You take that, or what they call the vector dot product, or just take your directional vector here, its unit amount, times your gradient vector here. So it would be 347.01 times points, and make sure they got material here. EXX, your vector for this same amount here, material, and then the vector for EY here was for labor. Make sure you get that. So your directional vector here for material, 0.6679 times your gradient amount, that's going to give you 231.77 here. Then you add to it, you take your gradient amount here for labor, 198.85 times 0.7442 here. The unit directional vector here for labor gives you 147.98. So you add those two amounts together, and this is what they come up with, the directional derivative, as they call it, or this directional vector here, 379.75. 231.77 plus 147.98 gives you that. So what you're looking at really is that's a proportional allocation here, a ratio of material to labor that you're coming up with here. So that's going to be your change. Now you could just put it in and look for your software package. In this case I use MapleSoft. You would have just put those numbers into it and would have come up with a solution here, 385.96 here, which I'm showing 379 here, but it's only because I didn't carry out the decimal points far enough here. Okay, so really you want to be looking at some software package here to come up with your directional vectors, or come up with the directional derivative, or that amount that we're looking at. So let's just go up and look at it here. So if we go back to our plot here, this based on our labor inputs here, our vector here, that was our gradient vector times our directional vector here, come up with, what was it? I think it was for labor here, let's look at it on this side. For material here, I think it was 231.77 here. So that's the length of that vector here. That's the material. That, remember, that was our gradient vector here of 198.85 times 0.7442 here for the directional vector for that amount. And then for the labor side here, our directional derivative, or vector here, was what? That was, in a way, it turned out to be 147.98 here. And then you're adding those two quantities together, you come up with labor here plus your material income, directional derivative 379.75 here. All right, so that's what we're talking about. The slope here, we're increasing. The slope here is mean we're adding to our profit here at a rate of $379.75 based on our material input and our labor input. But the key is, and maybe let's just go down and understand it here to understand what we're talking about. These two vectors here, these yellow lines here, they're sitting on some plane or some slope, and they're contributing to our maximum output here, because our directional derivative here is sitting right on our maximum output, our gradient path here. It's sitting on our path here because that's the way that was based on our targeted point here. So our labor vector here, let's just go down and look at it. So if we go down here, see our labor vector was that gradient amount, 198.85, times our directional vector unit amount, 0.7442 here, 147.98. That's shown here. And then for our material amount here, that was a gradient vector 347 times 667.6679, 231.731 here. It should have been 31 here. I did put 37. It should have been 31 here. Okay, so that's what we're talking about here when we're talking about the gradient here. The gradient is really gives you the amount in the greatest amount in a direction here, amount that you're looking at based on your production function here. The gradient is going in the based on your production function. It's giving you the amount of the greatest increase, but to determine your where it fits into the directional derivative is you have to work with your directional vector here, and your directional vector here has to be going in at the same point that you have your targeted output here based on your gradient vector. Okay, so that pretty much summarizes it. So we'll just go on and maybe we can just look at some further 3D examples here of this gradient vector. All right, now we'll just look at the power of computing here and how we could use, in this case I'm using MapleSoft here to understand, in this case we were looking at this gradient vector here or this gradient path. So here I'm just showing the production function here on a sort of a see-through grid here. And then we have slicing through here in green here, that's really that level curve at that specific output. And then we have this yellow here, that's just the tangent plane going through our specified output. So nonetheless here, just to understand the power of computing and how we can visually demonstrate our different functions in this case, and we're looking at the production function. So if we just move over here, back to our directional derivative here, which included our directional unit vector and our gradient vector here, showing them again here. And we had our material vector, directional derivative here based on a gradient, and a directional unit vector here for material shown here, labor shown here, and then this was our total directional derivative here. And then again, this orangish curve here was that level curve. And then showing our output here, where we had actually, we would start out with our units here at right over here and move up, but I'm just showing here how I'm showing total output shown here. And then just moving over here, just looking at a different profile again here based on that directional derivative and our gradient unit vectors here. And all I've done is just added in another 90-degree plane here, or a plane at our targeted output here, just to understand that it really doesn't add anything except looking at the plane here based on our looking at our production function, just looking at it straight down. And then if we go over here, down here again, just another side profile here of our production function here, shown here, and here's our gradient path in blue again, and then level curve here, targeted output. And then moving over here, and remember you can move these plots around any way you want here. Just another view here looking at our directional vector here based on our gradient and our gradient vectors here and our directional vectors here, coming up with our directional derivative, excuse me. Again, just showing a 90-degree plot slice through our targeted point here based on our level curve here shown in green. And then just finally showing at it another view here. So actually, you can when you're using this software package, you can turn these plots or these 3D dimensions in any view you possibly want. You can turn them any direction and anything. I've just picked out some here to get an understanding on what we're doing. So with the software here and our plotting, we can get a better idea what we're doing here rather than just looking at a bunch of mathematical numbers and different numbers here. We can understand and apply those numbers here to diagrams so we can understand what these different numbers and functions are giving us. Okay, so that'll conclude our discussion.